Hello and welcome to Beginning Electronics. And the magic we're going to do today is to see how the transistor replaced the radio valve, and we're actually going to build a real circuit with a transistor that actually works.
And on this program we're going to use a 6-volt battery, a breadboard, a high brightness LED, a 500 ohm resistor, a couple of bits of wire, and a BC547 transistor. And we're going to show how that transistor can amplify a current. In other words, take a very tiny current and allow that tiny current to control a much larger current.
Before we take a look at the transistor, the component that made the radio valve obsolete, we need to take a quick look at resistors again. Now what I've done here is I've taken two of my 500 ohm resistors and I've connected them one after the other across this battery here. Now that means essentially we've got 1000 ohms of resistance across here. That tells me, using Ohm's law, which I introduced in the last program, that if I take 6 volts and I divide it by 1000, that's going to tell me what the current is that's going to be flowing through here. Just a reminder of Ohm's law: the voltage divided by the resistance equals the current. If it was 1 ohm, it would be 6 amps, but it's not, it's 1000 ohms, so therefore it's 6 thousandths of an amp, or 6 milliamps. I can measure the voltage and check that my batteries are really giving me approximately 6 volts with my voltmeter. Taking the two probes here and just connecting them across these two, we see that the voltage reads 6.03 volts. Now what's interesting is, what do we think the voltage is going to be in the middle of these two resistors? Well, let's just take a look and see, and lo and behold, 3.1 volts. So here's the circuit diagram for that: our 6-volt battery here and two 500 ohm resistors connected in series. And yes, this is the point where we measure the voltage in the middle, and we find that that voltage is approximately 3 volts. So in other words, the voltage right here is half of the voltage as it was measured across the two resistors. So there's half of the voltages across one resistor and half of the voltages across the other, which, given that they're approximately the same value of resistance, you'd kind of expect that, wouldn't you? But what about if we had 3 resistors or even 4 resistors? Let's just change this configuration a little bit. Take a couple more resistors, bend the leads over like this, pop them in, and so now we got a big long chain of resistors that are all the same value of 500 ohms. And I'll just pop that negative lead back on there. There they all are, connected together in a big long line. And if I measure the voltage across the whole thing, 6.3 volts. If I measure the voltage in the middle, it's about 3.1. And if I measure the voltage across just one of these resistors, well, it's about 1.5 volts. In fact, all of them are, if I measure the voltage across each of those, each one has about 1.5 volts across it. So we've got these equally valued resistances that are all in series, and the voltage is divided equally across each of them. And that kind of makes sense, as they're all the same values. So here's the circuit diagram for that, with 4 resistors, and when we measure the voltage across any one of these resistors, we find it's about 1.5 volts. So therefore the voltage we'll measure just here will be 1.5 volts. The voltage we measure here will be 3 volts, and the voltage we'll measure there will be 4.5 volts, and the voltage we'll measure there will be 6 volts. In other words, the full force of the battery. So if you think I'm measuring always with respect to this point just here, so from there to there 1.5, from there to there 3 volts when it's across 2 resistors, from there to there 4.5 volts when it's across 3 resistors, and 6 volts when it's across all 4 of the resistors. Now, what if I was to take this 500 ohm resistor and this 500 ohm resistor, these two together, and replace them with a 1000 ohm resistor? Well, that would be identical to these two resistors, one after the other, because resistances add up when you have two, one after the other. So the 1000 ohm resistor would have approximately 3 volts across it, whereas the 500 ohm resistors would have 1.5 volts across them. And if we actually just take one of these resistors out altogether, and now we just make 3 resistors across the whole thing. And what do you think? What do you think is going to be the voltage across each of those resistors now? So we've got 6 volts, we've got 3 resistors. And here's the circuit diagram for that with 3 500 ohm resistors. And when we measure the voltage here, or we measure the voltage here, we find the voltage here is 2 volts, we find the voltage there is 4 volts, and of course it's 6 volts up here. So there's basically 2 volts across each of these resistors. Let's measure it. And it's approximately 2 volts. So not really a surprise, is it? So if you think about it, if we varied the resistance of one of these resistors, so say we increased the resistance of one of these resistors, then it would grab a bigger share of the voltage. And if we decrease the resistance of one of these resistors, it would grab a smaller share of the voltage. So that's an important principle to remember. When we put resistors like this in order to ultimately divide the voltage, we call it a voltage divider or a potential divider. And we use this concept quite a lot in electronic circuits. And now what I'm going to do is I want to introduce the transistor, which is, if you like, it's a, well, it was called the transistor because they sort of thought of it as a resistor that could change, that could be transient. It isn't strictly that, but it's pretty much gives you the right sort of idea, is that the resistance of the transistor, or the amount of current that flows through the transistor, can be changed. Well, we've seen this circuit before, an LED with its protective resistor and the power pack, the batteries in the background. And here's the circuit with my 6 volt battery, my light emitting diode, my 500 ohm resistor, and there we go. Notice the symbol for the light emitting diode is the same symbol as a diode, which you won't have come across yet, but you will later. And these little arrows indicate that light is being emitted. But I'm going to add something new into this circuit. I'm going to add in a BC547 transistor. As you can see, it has a flat face on one side there. And I'm going to just pop that into the circuit. So disconnect the negative power lead. And I'm making sure that the round face of the transistor is going to be facing you, the viewer, and pop the negative lead back in there, connected to one of the leads of the transistor. It's not very visible, is it? Let's put it just there so it's very clear. Okay, and you can see that the LED is switched off. Okay, so that's the circuit with just the light emitting diode. So how did we change it when we inserted the transistor? What we've done is we've, if I just give a little bit of a rub out there, give space for a transistor, and the transistor symbol, or at least an NPN transistor, which is what this one is like this, a little arrow here, and then another leg going up from there, and the base of the transistor.
Now the electric current in this circuit would, if it was switched on, be flowing through the LED, through the resistor, and between these two extreme leads of the transistor. By the way, this lead here on the transistor is called the collector, this one is called the base, and this one is called the emitter. And what's interesting about a transistor is that if there's a very, very tiny current flowing between the base and the emitter, then that very, very tiny current can switch a huge current flowing between the collector and the emitter. So what could we do to give us a small current at the base? Well, I've got a couple of pieces of wire here that I've stripped both ends there. I'm just going to pop one, connecting it to the base of the transistor like that, and I'm going to take the other wire and I'm going to connect it onto the positive power supply rail. So I've got these two wires here.
Let's make those into big blobs. Those are my connections, my pieces of yellow wire. That's called the collector, that's called the emitter, and that's called the base. So a small amount of current, when a small amount of current flows through the base down to the emitter, then a huge current will flow from the collector to the emitter. So we can actually perhaps indicate that by saying, okay, that's the current flowing from the base to the emitter, and this is not standard circuitry, and then that allows a huge current to flow from the collector to the emitter, and there's my huge current arrow indicating what's going on. So just filling it in there, one huge current arrow.
I'm going to just touch one of them with one set of fingers on one hand, touch the other one with one set of fingers on the other hand, and lo and behold, the LED lights. So what's actually happening here is a minuscule current, because as you can imagine, my body resistance is enormous, is flowing from the main power rail here through my body and back down through here into the base of the transistor, which is then switching the transistor on, or I won't say switching on, but increasing the current flow, or allowing a current to flow from the collector to the emitter that's a big enough current to actually switch this LED on.
So tiny current here, big current there, and the tiny current of course was with me essentially standing here. This is the circuit diagram for a human being, only joking, with my hand, one hand on here and one hand on there. So probably my resistance, that's 500 ohms, my resistance is probably more likely to be something like 500 million ohms. So a huge, huge resistance there. I think I should be smiling, shouldn't I, and have some eyes and a face. There we go. How's that?
This process is called amplification, when a very, very small current leads to a much larger current. And it's ultimately this process that made the radio valve obsolete. So now you've seen what an amazing device the transistor really is, and now you're in a good position for some of our future programs where we can actually put the transistor into some really useful circuits.